the things that I'm going to keep trying to stress to you is that time and distance doesn't have any objective reality. I mean, for you to say that you're, what, 16 makes no sense. Oh, sorry, 20?
Yeah, that's okay. You got it. Second try.
Right? I mean, he can't say that he's 20 years old. I can't say that I'm 46 years old. It has no objective reality. Right? According to this equation that we wrote last time, right? That the speed, talks about space and time, and different observers measure different spaces and different times. Time has no objective reality. Unfortunately, people think about special relativity, and what's the first thing they do? They think about, oh, it's this time and distance thing. Wrong. Because science is about measurements, right? Science is about using energy or momentum so that everybody measures the same energy, everybody measures the same time. We want to look at invariance. So, I mean, even though this is kind of fun, scientists typically don't use it unless they absolutely have to. And it's because you don't have objective reality. And so we're going to go through this, and it does set you up for when we get into calculating invariance here. And so from this, you can see that you have different time measurements. And so what I want to do here is that according to that principle of relativity, we want to talk about Lorentz transformation. We want to talk about space-time diagrams. And then we'll talk about applications. So then we'll start looking at consequences. And when we look at the consequences, what we should talk about then is we'll talk about something called time dilation, length contraction, and then the standard the twins paradox. We won't have a chance to really talk about some of these other things. But there's a section here that I really want to do. It's called space-time intervals. And it's a really, really fascinating way of how you look at time. And it would totally change your view of how you look at intervals. Let's start with Lorentz transformation. So when I look at Lorentz transformation here, what are we looking at? We always have two observers, right? Who's moving? You or I? Who's moving? We don't know. We can't do a single experiment. So what a Lorentz transformation says, if these two frames are invariant, how do I transfer from one frame into the other? And so I'm going to start using this notation, but let's get this notation clear because this is the whole crux of all of the problems in this chapter. Okay? I'm going to think about a light clock like I talked about last time. And I'm going to say that there are two observers. There's a frame that has a light clock. Right? So that means that it goes up and down. This is what I'm going to call the S frame, where the light clock is at. Okay? And so I'm going to have some observer in the S frame. And then I'm going to have a second observer not with the light clock. And that frame is going to be S prime. Right? And this is S prime here. And these two frames, we typically say that if there's relative motion between the frame where the light clock is and where the other frame is at, then we'll be looking at changes in time like we talked about last time. If there's no motion between you and the light clock, there's no change in time. You're in the same inertial frame. And so keeping these two separate and knowing which frame you're in and what frame they're asking for is of paramount importance. So let's go for it. So what we saw here is that we talked about Galilean transformations. And what we saw last time here is that if you go from S to S prime, we use the frame X prime, X minus dt. That's one way that we could do that. So if we measure things in the X and in the S frame, I can calculate the position in the prime frame. I could do just the reverse here. We don't need it. But if I go in the opposite direction, in this frame here, you can see that in this case here, now I wrote a prime here, I didn't write it last time. But the key in this frame is that t is always equal to t prime. What do we know? Well, we know these can't work. Why can't they work? Because we saw that moving clocks measure different time intervals between two events. As a result, these have to be modified. How do they get modified? They're known as the Lorentz transformations here. And just to give you a quick upshot here, I mean, these can be really tedious to derive, but essentially what you do here is that if you talk about a Lorentz transformation, these are not equal anymore. Right? Two different frames measure two different time intervals between two events. And there's an overall constant. And this constant they call gamma. Okay? And as soon as you do that, you have to look at events that are going to be measured by all measurers. Any event that, there's only one event that could be the case, the speed of light. All frames of reference measure the same speed of light. So you can set up a situation where you can solve these things. It's tedious. Actually, they're in my lecture notes and you can have a copy of them and you can see the details. You essentially look at spherical light shells that move out and all observers must measure the same spherical shell. Because the speed of light travels the same for all frames of reference. So if you do this here, you get these things called Lorentz transformations. And instead of deriving them, I'd rather just use them. Okay? And what you get here is that this is what you end up with. You end up with S going to S prime. By the way, in physics language, I don't think your book doesn't use this, but this is standard physics language. We say that if you want to go from S to S prime, they call it a boost, a Lorentz boost. But so if you hear me say boost, I'm boosting from one frame to another, that means I'm doing a Lorentz transformation. It's just, old habits are hard to break sometimes. Right? That's the way it is. And so what you find here is you get this. You get that X prime, you get this gamma of X minus gt, the Y's components and the Z components don't change. And this is for only motion along the X direction. And then you get a T prime